So the research project is called Pore to Wrap. It's a 4-year project funded by the European Union Horizon 2020 programme, and our role is to scale up a process of producing battery materials from starch. The process is a 3-stage process. The first step is to create a gel with your starch, which is just heating in water and you get a very thick gel. We then freeze dry that material to create a flowable powder, and then that powder is put through a furnace to produce your carbon support. The BDC, the Biodynamic Development Centre's role in the project is to scale up this process, which has been developed over a period of 10 years by the University of York, to produce materials at a volume sustainable for sending off to project partners, so talking about 250 grams up to 10 kilos. Historically, the process has been batch, and the aim for us is to move to a more continuous system if possible. So the material entering the furnace is an expanded starch. What we mean by expanded, we mean there's a spongy network, sort of porous network, which means that material is going to enter that structure and be used for batteries. Before we can be used for batteries, we need to put it into a furnace to carbonise, turn into a carbon. So we're going from a white material to a black material, and it's this black material which is then used for battery supports in this case.
Okay, well the main structural properties are pore size, pore volume and surface area. And what we are trying to do is we're trying to generate materials with very high mesopores in comparison to the more microporous alternatives. And that allows us to do a wider range of things within the larger pores. What we find is for battery applications, we want moderate sized pores but with a relatively large pore volume. For catalysis, it seems to be more larger pores are a little bit better. So we can tailor, hopefully, the porosity to suit the different applications that we're looking at. The overall aim of the project is to develop a sort of a commercially viable multi-kilogram per day process for making the materials. At the same time, from a research perspective, we want to understand the factors that produce the properties. So how do we control pore volume, how do we control pore size, how do we control the chemistry on the surface, so that we can decide on precisely the properties we need for a process, and then work out quickly how we make the material that will have those properties. So it's a combination of scaling up to a much larger scale, going from lab scale to kilos per day, but at the same time really underpinning the understanding of what generates the material structures. Okay, I mean, ideally we're looking to replace materials in things like energy applications, so lithium-ion batteries as catalyst supports. So there's already markets for these materials, and we would hope that we could use this as a replacement. So develop a company or a commercial outlet where we could sell these into those markets. The benefits is probably from the point of view of sustainability, in that we're using these materials from bio-based resources, often things like unavoidable food waste sources. So starch, for example, there's a lot of waste starch around. If we can convert that into components for batteries, components for catalysts, which then go on to make another range of useful products, then that's quite a big benefit, and that will move the things forward. Hopefully we can also improve the performance of materials so that we have higher performing catalysts, higher performing batteries, and potentially other applications in the future. The overall process is essentially 3 stages. The carbonization process is the final stage, and that's the one that really generates the material properties. So the early stages basically expand the starch to give it mesoporosity, but we then need to carbonize to get to the real material properties. So the carbonization stage is critical. It develops the porosity, it develops the surface chemistry. So lower temperatures it's more starch-like, higher temperatures it's more carbon-like. But at the same time we need to make sure the pore volume, the pore size, the surface area is developed in the correct way as well. and controlling the temperature and the heating profile to get to that temperature is absolutely critical in generating these properties, and therefore the furnace is absolutely vital to develop that.
So the furnace at the moment, we've run quite a few samples through, and it's been very comparable to smaller scale furnaces that we used historically. So knowledge we've learnt by using this furnace could be applied to a larger scale. Obviously there's material processing issues and furnace issues, but in terms of the furnace we can definitely scale up using this technology for the material. So because the furnace was funded by European money, we had to go through an open tender process. Carbolite were the highest scorers in that open tender, and based on the cost of the process and the expertise they would bring to the table through conversations, through the tender process and the written report which was needed, they came out higher scoring, and very knowledgeable about that process, and were able to use their own expertise to develop a furnace which is working now for us and being able to deliver the material we want. We would work with Carbolite Jarrow again. Their expertise and their knowledge to develop a furnace which can handle our material, which is a very difficult material to deal with the low bulk density, being able to produce, they've been able to answer our calls very professionally and timely, and be able to help us and actually listen to our problems with our material and come up with a solution which works very well and very comparable to the lab scale information, and we would recommend working with them again.